The title of today's webinar is GWAS on your notebook. That's Genome-wide Association Studies on your notebook, using semi-parallel linear and logistic regressions. And this presentation is our first international presentation by Karolina Sikorska from the Department of Biostatistics at Erasmus Medical Center in Rotterdam. Karolina also holds a master's degree in mathematics from a technical university in Poland, and she's working on her PhD at Erasmus Medical Center. I'm Sean Yarns, and I'll be your host today. I am introducing Karolina, and then I will be moderating a question and answer session at the end of her presentation. And so if you're interested in asking a question, if you look over at the GoToWebinar control panel, there's a questions box. And you can just type in your questions, and I will be reading those to Karolina at the end of the presentation. And hopefully she'll be able to answer your questions. So now I'm going to pass over controls to Karolina and let the presentation go. So here you go, Karolina.
Okay, thank you for the introduction, and thank you for the invitation to give this webinar. So I would like to emphasize at the beginning that this work has been done with Paul Eilers, who is my co-promoter in Erasmus Medical Center, and who was the first person believing and suggesting the GWAS on your notebook idea. And like was been said already, I will introduce semi-parallel linear and logistic regression, and this term semi-parallel will be introduced in a moment during my presentation. So our motivation for that work was that we noticed that typically GWAS studies are considered as computationally very intensive, and this led to so-called computing clusters. So because the job is so easy to parallelize, you can split it for as many processors, for many computers as you wish and can afford. And we also noticed that the data organization of the SNP data is not the most efficient when it comes to extracting blocks of SNPs. And I will explain everything, why is it so important for us to be able to extract those blocks of SNPs in an efficient and quick way. So our goals were to first speed up the computations, and we want to use matrix operations, and that will lead to the term semi-parallel computing. And in the next step, we have to take care of the data structure. So we want to rearrange the data structure, and we will use matrix-oriented binary files. And the bottom line is that we want to make GWAS computations feasible on a single computer. We want to show that they are actually doable within a very reasonable time frame. So before I start the real presentation, I will start with some technical details. So I use one desktop computer, 64-bit version of R, and during my presentation you will hear a lot about speed. So imagine you have n individuals and m SNPs, and it takes you time t to complete the job, which is measured by proc time in R. So we define speed as m times n divided by t, and that's the units of that would be SNPs times individual per second, so-called SNPs. And the numbers will be very big, so we will use megasieves. And we find this measure of sieves and providing the speed much more useful than just providing the computation time, because it is just very flexible to recalculate the expected computation time for different n and m. So I divided my presentation for 3 parts. In the first part, I will explain how to speed up linear regression. In the second part, we will discuss logistic regression, because there things are quite different. And I will close with the discussion about the data access and the data rearrangement. So starting with the first part of linear regression, imagine that we have a simple regression model with no covariates, so the common y equal to alpha plus beta s, and we are interested in the SNP effect, so in the beta. And in R, the most straightforward way is to use LM function in a loop. So how would we do that? In the first slide, I show how did we simulate the data and how are we calculating the speed. So first I simulate n individuals. So I set so-called mini GWAS with 10,000 individuals and M 10,000 SNPs, and I simulate my SNP matrix, simulate my vector of response. Here I want to measure time. I pre-specify my vector of betas, and then in a loop for each SNP at a time I fit the LM model and I save my beta in a vector, and then we measure the speed, and that was 1 megasip. So for 10,000 individuals and 1 million of SNPs, we would need around 3 hours on my computer, and you can keep this number of 3 hours when I will compare it in a moment to our proposal. Another thing that we can do is change the function in a loop. So instead of LM, we can use LSFit, fitting a least squares model. So everything stays the same. I'm not showing here anymore how we simulate the data. So I pre-specify my vector, and here the story goes the same way, just I'm fitting the LSFit function. And we see already that we improved the speed to almost 7 megasips. So just by simply replacing one function by the other, we can hugely speed up the computations. And now, for a simple regression model, we know that the explicit solution for the beta is very simple. And we can actually compute it ourselves without using any ready function to fit the linear regression model. So here I do the same story, just in a loop, one SNP at a time. I'm just calculating my beta myself. So before the loop I centered response because that stays the same. And here in the loop I center one SNP at a time, and I solve the model, and I measure the speed of 45 megasips, which is already another improvement. And now comes the idea of semi-parallel computations. So in the formula on the previous slide, we've seen that what is actually happening is that we have to center our vector of response, y, and center our SNP. And then what's happening is that the y part, the response stays the same. So I'm only changing my SNP. And what is actually happening is only simple multiplication and summation. So imagine that we want to take a block of SNPs. I take k SNPs at one time, and this operation of the beta can be done using matrix operations. So if I multiply transpose vector of y's with the whole matrix of the centered SNPs, I can get my whole vector of betas in using one matrix multiplication. And that's what we call semi-parallel regression. So we also get many betas in parallel, but on the same computer using the same R session. So that is the idea, and now we have to see how it works in R. So the easiest way would be to use function scale. So we first center our vector of response, and here we center the SNP matrix at once using function scale. And here I calculate the denominator, so column by column sum of squares. And the operation of transpose y with centered SNP is done using cross product function. And then we see that I achieved a speed of 32 megasip, which is actually slower than doing the explicit solution in a loop, which we saw previously. So that is a little bit disappointing, but that is also suggesting that clearly slowing down part is function scale. So what we wanted to do, we wanted to avoid that function. So in the next step, we center the SNP matrix ourselves. So we just subtracted the averages column by column using the outer function. And here we calculated the betas, and the speed increased to 130 megasievs. But looking further in the details, we saw that centering of the SNP matrix actually not necessary at all, because you see in the numerator you only have to center y, and SNP stays in the original version, and in the denominator we also don't need to center SNP, we only need the averages. So here you see that the most efficient way to compute the semi-parallel simple regression in R, and the speed was 220 megasieves, and now that means that for 10,000 individuals, 1 million of SNPs, I would need only a minute to do such a GWAS. And now compare it to the 3 hours that I mentioned on one of my first slides using a standard procedure. So the speed up is enormous, but I'm also a little bit unrealistic so far, because I'm only talking about the simple linear regression model. And normally in practice you will correct your models for many covariates, and when we want to correct for population stratification and we use principal components in the model, a number of covariates will grow to even 30 perhaps. And it's very easy to add covariates in the LM or LS fit function, but it will also of course affect the speed of the computation. So here we checked how covariates are affecting the speed. So for example, here for one covariate, the speed of 0.9 megasiev dropped to 0.3 megasieves for 30 covariates. So we want to deal with covariates in our semi-parallel computations in an efficient way, not to spoil our achievements from the simple regression. So what we do here, we introduce the new variables, a new SNP variable S star and new response Y star. And here you see the formula for those transform variables. And although at the beginning they may look complicated, but they are actually based on projections. So we just leave the parts of the variables that are orthogonal to the space spanned by a vector of by the columns of X matrix, and then we can show mathematically that the beta that we are interested in is a solution of the new model. It's the regression through the origin, and now the solution for the beta is even simpler because no centering is involved. So in R, here I again show how do we simulate the data. I simulated 30 covariates, and then the X is the covariance matrix, and we assume that we include intercept, of course, in the covariance matrix. And here I transform the vector of response. And we have to be careful when we do this data transformation, because if you just multiply matrix one by one as they are in the formula on the slide before, it will be very inefficient, and you also may run into memory problems when you multiply n times n matrix. So here we show how to do those transformation in the quickest and efficient way. And here we transform the SNP matrix and know that everything goes in a semi-parallel way. So I transform all the SNP matrix at once also. And here I compute the vector of betas. Also, so far I haven't mentioned anything about standard errors and the p-values, and the p-values are actually the vital point of GWAS studies. So once we have this transform model with no intercept, it is very easy to calculate the standard error of the beta, and we already see that it will be very easy to semi-parallelize the computations. We also have to compute the variance of the measurement error. And here we should remember that although we have regression through the origin. Our original model included intercept and k covariates, so we should correct for the correct number of degrees of freedom. However, assuming that the n is very large, it won't have much influence on the final result. And we see that the residual sum of squares is also computed very easily using basic matrix operation, and it's very easy to semi-parallelize it. So here we see how do we do that in R. Actually, every operation needs only one line of a simple code. And here I calculate the p-values based on the normal distribution, and we take the lower tail to avoid numerical precision errors for the very small p-values. And in the table, you can see the final speed comparisons. So we see that LS fit function is indeed faster than LM. However, the computational benefits start to disappear once the number of covariates is increasing, and our semi-parallel regression is working 40, 50, 60 times faster. And now we can do the GWAS for 1 million SNPs with 10 covariates within 5 minutes, and that's already for beta standard errors and the p-values. I want to mention a little bit the missing data. So once you have missing response, it's not a problem, because that means that the whole individual is just removed from the analysis. But missing SNPs are more difficult to handle because in principle you can't have any NA in the SNP matrix, because once you have any NA, the cross product will return the NA value for that beta. So our solution to that was to impute the missing genotypes with just the average of the available genotypes. And we did a small simulation experiment that for a reasonable sample size for GWAS around 1,000 individuals and a missingness rate of 5%. It works very well. So here we see our p-values, and they are almost exact. And above that missingness rate, the SNPs are deleted from the analysis anyway. And in general, we don't see missing data a big issue, because nowadays the whole idea is to analyze the big SNP data which are imputed, and there we don't have any missing genotypes. So that was the linear regression. We showed how to semi-parallelize it in an exact way. And now I will discuss the logistic regression. So let us look at the simple logistic regression model without covariates for a moment. And again, we are interested in the SNP effect. We are modeling the probability of success. And logistic regression model belongs to a generalized linear model framework. And those are typically fitted with maximum likelihood. And a maximum likelihood is an iterative procedure. And it's of course then slower than fitting least squares. And because it's iterative procedure, we won't be able to exactly semi-parallelize it. And our proposal here is to think about maximum likelihood estimation as iteratively reweighted least squares. Before I come back to our idea, I want to measure the speed of logistic regression in R. So here I again simulate my SNP matrix, then I simulate the 0, 1 vector of responses from a binomial distribution. I pre-specify my vector of betas, I measure the speed. In a loop, I feed GLM function specifying the correct binomial distribution and the logic link. And the speed was 0.2 megasip, which was indeed 5 times slower than LM function, for which the speed was 1 megasip. So coming back to iteratively reweighted least squares, we can write maximum likelihood equations for the t+1 iteration as weighted least squares. And here our Z is our new response, which is based on the observed zeros and ones and the probabilities. And once we have the solution, it's very easy also to calculate the standard errors. And the W matrix here is the weight matrix, which is diagonal matrix with P times 1 minus P on the diagonal. So here I want to show how we can solve logistic regression model using iteratively reweighted least squares approach. So I have to start with P somewhere with my probabilities. So I just take the sample mean. And here for 20 iterations, and normally 20 is more than enough, I calculate my weights. I specify my weighting matrix. I calculate my Z, so the transform response, and here I fit the weighted least squares, and I update my solution, and I calculate my new probabilities, and that story goes for 20 times. And you will see that normally after 4 or 5 times nothing is actually changing anymore. And at the end I'm calculating the variance covariance matrix. But still, given iteratively reweighted least squares, in such a form we are not able to do that in a semi-parallel way. Because in principle the SNPs, the weights are different for all the SNPs. So now the approach here is to rely on the fact that in GWAS all the SNP effects are really small. So you can learn as much as you can from the model without the SNP. So we fit the model without the SNP, we take weights from that model, and we assume that they are almost final, and the SNP will be only a small perturbation to that model. So I start with the case for model without covariates. So here I explicitly write the solution for weighted least squares and for the standard error. And if we don't have any covariates, all the weights are the same for all individuals. So Wi can go in front of the summation, and a lot of things are simplifying, and then you can easily see that the formula for the beta is exactly the same like for linear regression, and the formula for the standard error is actually even simpler. So here I do that in R in a semi-parallel way. A lot of things stays the same like in linear regression. Here I am specifying the starting point for my probabilities, which is just the average because no covariates are involved. I calculate my weights and my transform variable, and here I'm doing the centering, and here I'm avoiding the centering of SNP. And then again, using cross product, I calculate all the betas at once, and standard errors and the p-values. And the speed was 150 megasievs, which is more than 500 times faster than GLM. But like I mentioned, this is not exact solution, because in principle, we assume that the weights we took from the model without the SNP are almost final. So we have to investigate how precise we are and how actually the approximation works. So we took the sample size of the typical GWAS, say 2000, and we simulated the odds ratios for the SNP as a random number between 1 and 5. And we assume that this is already very optimistic interval for the GWAS. And we fitted GLM model and our semi-parallel approach, and we see that for the area typical for GWAS up to odds ratio 3, we are actually exact. And of course, in the higher range of odds ratios, we will underestimate the odds ratio, and we will also underestimate the standard error. So the the p-values would be too optimistic. But like I said, in the typical GWAS framework, our approaches can be treated as actually exact. We have to deal also with covariates in logistic regression, and we want to deal with them in a similar way than in linear regression. The only thing that we have to incorporate is this weighting matrix. So here we again do the transformation. And once the transformation is done, we have very simple solution for the beta and for the standard errors. But here we have to remember that weights are different between individuals because of the covariates. Here I show how to do the full logistic regression in a semi-parallel way in R. So I'm fitting GLM model once, omitting SNP. Then I'm taking the predicted probabilities and I build the whole model. And here I'm transforming again in a careful and smart way. I'm doing the data transformation. And here I calculate my vector of betas and standard errors and the p-values. So the final comparisons of speed show that the benefits in the logistic regression are much higher even than in the linear regression, because GLM function is much slower, and our approach is actually very similar to linear regression, and in a way is even simplified when you want to calculate the standard errors. So, for example, 1 million SNPs with 10 covariates can be analyzed using logistic model within 5 minutes, and compared to 28 hours that you would need if you apply the GLM function. So I introduced the whole idea behind semi-parallel computations for linear regression, where we can do that exactly, and for logistic regression, where we do that approximately, but in a way also almost exactly for the GWAS framework. But in previous examples, I used the simulated data, so I was simulating a mini GWAS, and that's not what will happen in practice, because although we can do the computation very fast, but first we need to actually have the data in our software before we can do the computations. And we know that SNP files are very large, those are many gigabytes. And even if we use a 64-bit version of R and we have reasonable RAM on our computer, we won't be able just to load the whole file at once into R, and besides that would take a really long time. So we have to work with blocks of SNP, so we have to be able to read in a very quick way a block of SNP for all individuals, and the size of the block will of course depend on the memory that you can spend on it. And in our experience, people work a lot with MACH files coming from the imputations, and those files are just text files, and typically we see that they are written as row per person. So all the SNPs for one individual are written in a row, and this file is just written as one big chain on a disk. And in this structure, all SNPs for one individual are saved as a record, so they are very close to each other. But if we would like to access the blocks of SNPs for all individuals, they are so far away from each other that would need really long time. And it's also very difficult to read blocks of SNPs from such a text file structure. So in principle, we could transpose that file and write it as SNP per person text file. And then we could use function scan in R to just scan it row by row. but it doesn't seem like a very efficient solution to just transpose one text file to another text file. Besides, function scan, it's not quick enough for the GWAS computations. So our proposal here would be to move to binary files, because we know that they are much faster, and you can easily create them in R using write bin and read bin. But those files, the basic binary files, they work on vectors. And then again, we have a problem of row per person structure, because we will save it in a more efficient file, but still extracting blocks of SNPs will remain a computational issue. So here the most efficient way and the solution for that is to use array-oriented binary files. And there are many options in R available as files become more and more popular. And matrix-oriented binary files are saved column by column. So now you can save it in such a way that one SNP for all individuals will make a record on a disk. So it's very easily accessible. And I tried many packages, and I found NCDF and FF packages most useful. And NetCDF data format is already existing in other areas like meteorology, but now in the last couple of years it has been implemented as a R package, and it's working very well. And the FF package, although not created for the genetic area, for me it is working very efficiently. So before I start with the packages, I want to visualize what we need to do with the data. So the top structure is what is given in MACH file, and in the bottom we see the structure that we want to achieve. So you see that a lot of shuffling and ordering and rearranging needs to be done with the data. So that will involve a little bit of work. So starting with NCDF package, first, given a MACH file, we want to write it as another object, as a matrix binary object. So of course you first need to load your library. And here I will use the simulated data. So I assume that I have a MACH file for 10,000 individuals and 100,000 SNPs. So that builds one chunk of the genome. And although it's only a chunk for 100,000 SNPs, I'm still not able to read such a text file at once in my memory. So here I assume that I will have to read blocks of individuals, and I will be saving them in the NCDF object. So I specify the size of the block for individuals which I can afford, and that's 1,000 individuals, which is my small n, and the capital N is the whole sample size. And I have 100,000 SNPs, and I simulate a block of 1,000 individuals and 100,000 SNPs. Here, when I create my NCDF object, we have to specify the dimensions, so number of individuals and number of SNPs. I have to specify the variables. So it's my SNP variable, and it is very useful to take care of some small details like saving SNP as a short precision number instead of double precision number, because it will save you a lot of space on the disk. And we can here multiply our SNPs by 100 and save them as short precision number. And after analysis has been done, we just divide our betas by 100 and we don't lose any precision. Here I create my object with the specified variables. And here I'm saving the data in blocks in a loop. So I specify which individuals I'm saving, and I am putting variable in the NCDF object. So I'm starting with cave individual. I save a small n, so 1,000 individuals at once, and I'm saving from one first SNP, I'm saving all the m SNPs. And that goes 10 times in my case in a loop, and I have to close my file after everything is saved. So it took me around 10 minutes to save such a file on a disk, and I found SSD drive very helpful. It was working much faster than using a hard disk, or especially if you use the network drives, they can be very slow. But remember that I am simulating the data, so it's not yet the final time, because I simulated my block and I was constantly saving the same block in the object. But normally what you would need to do, you first scan the block of your MACH file, and then you save those individuals in the object. So you have to add the scanning time in the whole estimation. And like I mentioned, taking care of details, it's very handy, and it can save you a lot of space. So once your file is created and you want to do GWAS, again I am reading the library, and I have to open my file, which takes just a second, and I'm specifying the sample size. So I have 10,000 individuals, 100,000 SNPs, and here I'm specifying the size of the block, but this time for the reading is the size of the block for the SNP matrix, so it's the M1. And here in the loop I will be reading blocks of SNPs, so it's also very straightforward, just get variable instead of put variable, and I have to specify where do I start. So I am reading first individual to, I'm reading n individuals, and I'm reading from the cave SNP, I'm reading my block size, so 10,000 SNPs. And we measure time, how long does it take, and it takes around 4 seconds per block of 10,000 SNPs, which means that for 1 million I would need 400 seconds. And just to mention that the computations would take around 200 seconds for that file. And one other thing is that I used here the proc time with index 3, which measures the elapsed time, because it is when it comes to computations, the user time and the elapsed time are almost the same. But when it comes to data access, it is more honest to talk about the clock time, because it's a lot of waiting involved. So that's why here we measure the proc time with index 3. So the second option was the FF package, which works very simply and actually maybe even easier than NCDF. Once you understand the tutorial, which is maybe not the easiest one to go through at the beginning, but later on things become very clear and very straightforward. So I use here the same idea. I have to create my FF object. Again, I use the tricks of specifying SNP as a short precision number. I have to provide the dimensions of the file, and I'm saving the data in blocks. And the FF package works on matrices. So actually in R, once you specify your FF object, R is treating it as a matrix. So once I want to put the data in that object, I just have to specify which rows and which columns am I filling in. So that's even easier than in the previous package. And then at the end I have to finalize my object, close it, and it is very useful to save it in the R data object. And that only takes few kilobytes, but it is very useful. And it is useful here in the once you want to read the blocks, because if you start with loading this R data object, R knows what kind of object are you talking about, and it knows where is it, and you see that it's in the list of the objects in the workspace, but it only takes like a second to load it. And then in the loop, you only have to specify what part of the file you want to grab for the analysis. So again, it works exactly like on the matrix. So I'm just saying that I want all individuals and my block of SNPs. And for me, this package worked faster than NCDF. Both saving and reading the data was around twice faster. And also know that it is very easy once you have such an object to extract just a single SNP or a group of SNPs for the further analysis, and or if you want to have a closer look in your data. And in our experience, getting chunks or getting random SNPs in the current MACH file structure makes it very inefficient, and we have to wait a really long time before we get our data. So I just want to summarize the presentation. So we showed how we can make the GWAS computations easy, and actually they are feasible in the notebook within very reasonable time. And I also illustrated that if you don't take care of the data access and the data structure, this part can be a real bottleneck to the whole method. But if you start using matrix-oriented binary files, the problem is solved. And more details about the whole idea is in our BNC bioinformatics paper, and the codes that are partially here are also available on the Bitbucket. And thank you for your attention.